wrap it up. Remember the PMOS here? Why is it special? This one. What is this one doing? Remember we were here on Monday and you got confused and it was a time to call it, right? So we overlapped. So what's happening here? Remember, if you toggle, so when it pulls, right? It pulls a VDD minus VTHN, right, to this cap. When this one pulls down to ground, it pulls current down. So on the top, it charges up on the top because it is open here. Whenever this one pulls, this one pushes up. So it's going to charge up this one a VDD from this side. So VDD will be stored here, which is able to pass VDD minus VTHN to here. And it's going to stuck. Why it's going to stuck? Same place to stuck. All right. What's here, and VDD. Oh no, they're shorted. Sorry, clock knot is here, right? So when this part being pulled down to ground, it sources current from here and charges up to VDD minus VTHN. And if this one goes down, this one goes up, right? It's a rising edge. It charges to VDD from the clock. So VDD will be here. And this NMOS will be opened up by VDD. Okay, so whenever a rising edge arrives here, it's going to add another VDD to it. Why? Why it's not losing? Okay, so is it going to the gate? No, it's a dielectric material. It's not going. So what about here? If this channel is opened up, right, possibly it's going to short this pin to VDD. It's just a wire, and this is a very strong power supply, okay? So whatever charge is stored here previously, if you have this channel opened up, it's going to short to VDD. Why not? Because you didn't open this gate that much. It's not transferring the 2 VDD minus VTHN is a pretty high voltage to here. It's not able to do it. You remember the NMOS is bad at passing what? VDDs. So now if you flip it, okay, you treat this point as a power supply, you just open it up with a VDD, just one VDD. Wait, it's not even open.
Yeah. It's a higher percentage. No,
it won't open anymore. Is it going to open? Still open? It's not. Because no, whenever this was VDD minus VTHN, it is still open because VDD minus VTHN, which is VTHN, right? It's still equal VTHN, so the channel is still open. But however, whenever this one is a rising edge arrives, it's going to pump another VDD here. I just adding like superpositions, adding to this point. You are getting 2 VDD minus VTHN, and this one's off. It's not on anymore. It's nowhere to go. Not going to the gate. It's not going to the channel because it's off. No, it's not. It's not going to the gate. And this pin connect to the right hand side, right? So this voltage is shorted to a NMOS And then there's a PMOS. Has a bulk connect to the source. Yeah. So what's the largest voltage you can expect over here? Wait, did I do it right? Probably didn't do it right. Did I? Yeah, that's the point. So you can get the whole VDD here, right? That's the point. So this PMOS will be, so the source here will be a VDD, and wait, it's a VDD or larger than VDD? Let's see. Yeah, it's gonna be larger. Why? Yeah, because the sample, this is superimposed to that VDD, the signal, right? Yeah, but later, yes, but eventually the sample, the sound wave will pass through this transistor and arrive here and charge up this cap and adding, because this one will be off whenever it's doing sampling. So there's nothing here. It's going to be a floating VDD. Remember, that's a key point. That's the most important part of the circuit. What is that? It is making a floating VDD across this cap. That's the whole point of this circuit here. It's making a floating VDD across this, the two terminals of the cap. So whenever it's adding, it's so the voltage in or the analog voltage arrives, it's going to be superimposed to that VDD, the DC voltage to the cap. It's adding to that VDD. Whatever arrives here or across the two terminals of the cap, it's going to be VDD plus that amplitude of the sound wave, which is exactly the voltage here to here. Okay, that's the difference between the 2 points. And because this is the PMOS, and this part is VDD plus the sound wave for this node, right? And whenever this PMOS is on, it's going to pass through here. And which is exactly VG, which is a gate voltage for the sampling NMOS. And because whenever this is on, whatever here will be passed to here. So as we just said, right? So this cap is holding an amplitude of the sound wave and the VDD. It's going to be the same voltage here as well. It's being applied to the VG. So VG becomes VDD plus sound wave. And this is the sound wave. So VGS becomes VDD. So it's not changing VGS. That's a key point of this circuit. Why we don't want to change VGS, remember? Yeah, short answer is to reduce distortion. But how the distortion happens? If you do not use all the circuit here, right? Just use a sampling circuit. How is that? Is that going to work? So here's V in, right? That's a sound wave. And I just turn it on, use VDD. It's VDD. And here is a holding cap. If I turn it on, I hold it here. Okay. Oh, now if I turn it on, I start charging up the cap. It's not holding, it's sampling. Why is this introducing distortion? Yeah, VGS is a variable, and the channel resistance. So VGS is a variable of the channel resistance because you are not opening up the channel as a constant. So it's changing the resistance here. Because remember we have learned all these RC circuits. If you have a different Rn here or the channel resistance, it's going to change the time delay when the signal arrives here. If you have the same delay, got a sine wave, right? Delay every point, voltage point by a constant. It's like shifting everything to one direction. You are still getting a sine wave. It's okay. But if you got, whenever the voltage is different, you are getting a different time delay. So you are shifting the points to the right or delaying every voltage point with a different time delay. You are getting distortion. It's not a sine wave anymore. It's something else. So you want to keep a VGS to be a constant. How? Right? So VDD plus V in minus V in is still VDD. It's always VDD. That's the whole point of the circuit. So when you do the layout for all the other parts of the circuits, it's pretty straightforward. Just most of the PMOSes. What about this one? You see the bulk, all the other bulks are being, the NMOSes are being shorted to V lows, and PMOSes are V high, right? Just the power supply. But how to do a layout? That's my question here.
State diagrams.
Let's see. Let's draw some figures for the cross-sectional view of the NMOS of the PMOS. Still remember what's that called? Body effect for NMOS. To make the answer shorter, to handle any interview questions like that. When it's getting a body effect for the NMOS, when the body effect will happen for the NMOS. Yeah, you got a VSB. This is VSB, right? Because S is higher voltage, B is lower, so it's VSB. Because NMOSes attract what in the channel to form a channel? Electrons. And this is a higher potential, right? So the electron is going to move. So I need more voltage to turn it on. For PMOS, it's VBS. If there's a VBS, because PMOS attract holes to form the channel, and this is lower voltage, so the holes are going to move to here, right? So the best way to avoid that is just short these two together. And for that PMOS in the 7-hole circuit, what's happening? If you have the layout for everything in the overall layout, remember these are the body contacts and shorted to VDD for the PMOSes, right? Remember on the top rail? They are not just a wire. You didn't use the metal for the rails, did you? What are they? For the PMOS? Yeah, they are NMOS. There are these ones, these nodes, right? Like N plus. So these nodes, you pick them up from the library on the left-hand side of the electric VLSI software, right? And it has all the contacts and has a green color behind it. So what's the green color behind it? Or all the dots? That's diffusion, which is N plus, right? What are these ones? Vias and metal 1. Okay, it's via and metal 1. And they are directly in the N well, remember? It has a diffusion, the dots, right? They are in the N well because it's directly from the library. They should. And then you have a NMOS here, a PMOS, sorry. The PMOS is in the N well as well, right? See? If you have a gap here, what's happening? What's really happening? If there's a gap, do we want a gap here in between? No, you want them in the same unwell. So eventually, after you finish the layout, usually you just draw a pure unwell layer to cover everything, just in case there are some gaps was not covered by the unwell. So they're in the same unwell. So what about that transistor? What about that NMOS? So this, sorry, PMOS. This PMOS has a body contact, right? Is that body contact shorted to the same in the same unwell? No, you got inverters here. There are only two, I guess. No, these inverters. Yeah. It's hard to lay it out in the circuit here. So there might be so all these other PMOS are in here in the unwell, right? And when you do the layout, you short them together. You short the source to VDD because the VDD are so the sources are connected to VDD, and also you want an N plus connect to VDD as well, so they are shorted together to the same node. But that PMOS has its own, is in the separate unwell. It's here. And has unwell. How to short it to VDD? Is that short to VDD? It's not. So no, it's not going to VDD at all. So the bulk is not shorted to VDD. If you just look at circuit, right? So it's shorting the bulk to source. And that's it. So you don't want to put in here, so just short the bulk, which is, you need another thing like this, right? Just grab it from the library. But it's not short to VDD, right? You just have another one, which has this, has a diffusion, and short the source to here. And these, that's what I'm thinking. So if this one, if the source is larger than the bulk, but the bulk for all the other part of the PMOS is all the rest of the circuit is shorted to just VDD, right? It's not higher, just VDD. But for the bulk or source here, it can be higher. So it's not the body effect anymore, but you don't want that happen as well. So for example, if you have a VSB is a body effect, right? What if you have a VBS here? Well, yeah, it's going to leak current from the body to here. It's not desired as well. But if you just look at circuit, what's going to happen if you have the body contact here shorted to the same bulk voltage, which is VDD, right? And this one becomes higher than VDD. What's going to happen? It'll link to where? To VDD. Instead of going to here, it's going to link to VDD. You couldn't see it here in the schematic. Did you get that? Because all the PMOSes, we don't do the layout, right? All the PMOSes have their body contact, which is these ones, shorted to VDD, because you just label that top rail as VDD, right? And this one has a bulk connect to source, and you don't want the whole thing has an overlap, so the unwell has overlap with this one, because whenever there's an overlap, the N plus here will be shorted to the N plus here. Why? They're in the same unwell. It's going to be the same potential.
The two on the right should have.
It's just an individual unwell.
Right.
No overlap, right?
Right.
Just an individual.
Two need to be in
Yes.
Okay.
Why? That's how I drew it here, right? The bulk is shorted to the source, and so the bulk connect is N plus. Because N plus is in N well, so that's why N plus is the body contact. So these are in the same N well because the source and the bulk, they are shorted together, right? But there shouldn't be any overlap between these two. Make sense? No? Yeah. Yeah, so in the future, it's not the only circuit having this problem, but if like all the charge pumps, they have a higher voltage than VDD, they may need their own N wells, individual N wells for that part of the circuit.
So that just takes up more space on the chip, right?
A little bit, gotta ignore that, it's tiny. All right, a quiz question here. What's the highest voltage could possibly be here? Yes. All right. Okay. And I don't want to keep this one in the same N well as all the other PMOSes because what? Because of what? Yeah, that's ESB for the PMOS, right? It's not body fact. It's another direction. It's the opposite direction of the body fact. So because whenever this there's no VSB. Is there a VSB? The B is shorted to S. For this one, is it? It's just linking to VDD. The voltage is going to link to VDD. If you put this one in the same, yeah, let's move forward after this. Okay. All right. So if the voltage here, right, because the source is shorted to the bulk, this PMOS is the special PMOS we have on the circuit, right? Okay. If the voltage here higher than VDD, it is going to be higher than VDD, right? It's VDD plus the sine wave. And if you keep this PMOS in the same N well as these PMOSes, it's going to be VDD plus something, which is higher than VDD. So it's going to leak where? It's going to leak to VDD. So you are leaking currents to VDD, to the power supply, not going to the right-hand side. The purpose of this circuit is to pass whatever here to here, not lose anything, right? So that's why you have to keep these PMOS in the individual N well instead of a shared N well with the other PMOSes. Right, we'll talk about this later next time. You probably need a quiz on it.
Okay, yeah, please. Okay.
Right.
Yeah, I guess so.
CDAC is very simple as well. It's just capacitive DAC. I got an NMOS here to reset everything. And got a C here shorted to ground. And one more C. That's one of the digital pin. Still C. And then 2C. Same voltage, just on and off, right? 1 and zeros. It's 2C. 4C, that's V out. That's a CDAC. Now you can turn this on to reset the voltage and, just bring everything to the ground. So reset it to 0. So what's happening here? If there's a voltage, if you turn this on, for example, but keep all the other ones at 0, it's going to charge the capacitor. And remember, Q equals V over C or Q equals VC. Which one? Charge. How to remember that? Q is on the top. That's two assistants. One is called Victory, one is called Charlie. Charlie. It's a castle. So that's a queen on the top, okay? Victor and Charlie. Okay, so Q equals VC. So if you got a 1C here, what is Q? If the voltage charging up, what is the Q being contributed to this node? VC, right? But eventually it's being distributed to all the other C's. So what's VL? Q over C total, right? Which is VC over 1, 2, 4, 8 equals 1 over A C V. So this, if this is turned on, it contributes a 1 over A V, which is the LSB. This V, because this C is combined with this V, so that's why when this V is charging up the cap, it contributes VC to this point. Like superposition, right? This one contributes 1 over A V. What about this one? Oh, the other ones are zeros. This one, you got a rising edge here. So Q equals 2 VC. Okay. So VL equals Q over C total, right? What's C total? These are in parallel. So C total is not changing, right? It's 2 VC over AC, which is 1 over a quarter of V. So this one contributes this much. This one contributes this much. And this one, you can do the calculation, it's going to contribute 1/2. A half, right? Because it's C, it's going to be 4 VC over AC. 4 VC over AC. What is C? Cap, right? I'm just testing to see if you guys are still awake. But does that make sense? It works. Let's do a simulation. That's the best part of the simulation. It's a lot of fun, right? You can verify immediately after you do the calculation. I got a C5. Oh, that's C, 2C, 4C, that's AC. I just add one more bit over here. This is a 5-bit DAC or 4-bit DAC. Yeah. So you are awake. What is this one doing? Reset. Cool. Good job.
I did reset my 6Z. That's what they all say. Yeah. I meant to ace the exam. I just had a question too long.
What's next?
You right click and you hit X's.
No, it's just Pro VL.
I'm used to not having the stuff. Now I go through and add the offline.
What do I have for the inputs? And is this making sense as output? What is this thing here? Like crash of the stock market, right? Yeah. So it's going to 0, which is great. And then start adding up. So I designed all the sequences. So let's take a look at the voltages. What are they? What's the sequence of them? All right, kind of probe them. So I'm dividing the frequency by 2 for each of them, right? It's very easy to make in a Gauss function. You can see that, right? You can see the colors. Okay. So here is what? 0, 0, 0, 0, right? If we count backwards, it's 0, 0, 0, 1, and 0, 0, 1, 0, and 0, 0, 1, 1. So it's counting up. So if it's counting up, it makes sense, right? So you're getting this analog output, it's DA. Every time we add one LSB to it, okay, each time it's adding one LSB. Yeah, the simulation is always like that, but I think there must be a way to remove these ones. Okay. It's adding 1 over. Yeah, so 1 LSB is what? It's 1 over 16, right? 1 over 16. 4-bit, right? 4-bit is going to be 1/16, right?
Yeah.
Let's probe it, see what's going on with the voltage here. That's 62.13 millivolts. 1 over what? Yeah. Yeah. 1 over 16, right? Yeah, the voltage, the VDD here is 1 volt. Okay, so it works, and based on the experience from last year, we plugged it into the ADC, and it didn't work as expected. I don't know why. We were trying to add buffers to it, was not able to drive it. So, but it works perfectly individually.
So why don't you use an R2R ladder? This seems way smaller.
Yeah, and this one consumes less power because it's not static. It only detects the change. If you have R2R, it's always always on. If the resistor is just always on, passing DC voltages, right? These are only the edge spike that's going to store there and hold it. So this is, I think this is better. If you look at all the other references, they use this one more often compared to the R2R ladders. Consume less power, and I think we have introduced pretty much everything for the project. You guys should be ready to do it, to start working on it. Let's see. So we got something to cover today, and then a couple more lectures. I'm thinking we probably should use one of the lectures to practice on the wire bonder, right? And then, yeah, maybe next week, Friday or Wednesday next week.
What's the presentation?
Oh, the present, yeah. Yeah, I'm gonna delete this one. It's not making sense. But next Friday will be the first presentation, okay? Ignore the first one here. I'm gonna change it, reduce it to 3 instead of 4. What is that? Oh, here, this one. Yeah, yeah.
We have to do the first one that we didn't class.
What do you mean, the first one?
Did the presentation for this one?
Oh,
We already did it.
no, you don't have to present anything. But that's a simulation, right? You have to run it because you have to use, it's not wasting any time. You have to use one of these. You got to use one of them. Probably just pick up one of them, right? But for the homework, you have to do both.
Yeah. So might as well just do.
That won't be that difficult, right? Just verify the logic. And what about the second one? That's the SAR logic, right? Once you build that one, you can put it in here and simulate it. So this is a very nice simulation to verify the SAR's algorithm. Okay. Anything else we are missing here? So if you look at the diagram, sump and hold, comparator, yeah, comparator have to figure out a way to use. I don't want you guys directly use the ones I provided. It's from the textbook, right? So the comparator, I put it here. Model files is somewhere on this page. Okay, if you directly use it, we are not gaining anything, even though it eventually fails. I think we're still learning something, right? Just use a clocked comparator. It's a very simple circuit to build. So I don't think you need the ones I think I probably posted the link to here anyway. Yeah, clocked comparator sync files. You guys are spoiled. So it's here. You can directly use it. But the only ones to remember, whenever you are expecting zeros, it's oscillating, right? Have to modify the clock to make it work. And the reference is this one. Okay. If you use a comparator we used last year, your plug in is going to work, no problem. But since I want to change it, let's use a newer one. And another thing is the timing. I haven't talked about that yet. Timing. So that's a clock for the sample and hold circuit. So here's being, sample and holds VG here, right? That's VG, so the VG minus V in is always VDD. So the gap here is always VDD. It's verified. Okay, so we got a consistent VGS for the NMOS. First semester of the junior year. Right. Yeah, when I was in my PhD study, I used to stay up for the whole night for a couple times, and I hate it. I don't think that works at all because the lack of.
Doesn't really help you think anything.
Yeah, because sometimes you are working on a project, is because of lack of information, lack of instruction, have to keep searching for things. So the time you spend on it is not worth it. It's not like you are spending time to learn a lot of things.
Yeah, you're spending more time
To search. Yeah, because you lack of instruction, right?
Yeah.
That's bad.
Yeah.
I don't think so. I don't think so.
Yeah.
Let's talk about the timing because you guys will start working on it right after this class, right? So here's the timing. I got a counter here. So if you look at how to design the whole circuit.
All the clocks are the same, right?
No. You need a timing. You need a timing circuit to feed the clocks to different parts of the circuit. So sample and hold need one clock because you sample it and you hold it, and then you sample you hold it. So that clock shouldn't be 50% duty cycle. Why? Why you don't want a 50% duty cycle for the sample and hold? Yeah. Sample it, and then hold it. So that downtime will give all the following circuit enough time to the conversion, like the 9 cycles, right? So if when we were looking at this circuit at the beginning of the class, right? That's a clock. So this clock shouldn't be 50% duty cycle. We want to save the time for the conversion, not the sampling. The sampling is rising edge samples. See? It's okay, but you shouldn't do that, right? So if you look at this one, that's a clock for the sample and hold. You can see it's being held after that. But the rising edge does sample it. Why is sampling it? How can I tell it's sampling it? Yeah. So the rising edge here is samples and tracks actually. And then whenever the falling edge arrives, it's going to hold it. I think I have a zoom in. This is zoomed in figure of the same diagram on top, right? So see here, sample, and then start tracking. It starts tracking. Why is tracking? Which is the signal? No. Yeah, blue is a clock, right? It's like a 10% duty cycle clock. And this is the sound wave. I just zoomed in, right? And what is this one? The output of the sample and hold. So it sampled it and then track, or sample and track actually. Sample, track, and hold. Why is tracking? How could you tell it's tracking? Let's answer the first. Yeah, so there's overlaps. They're overlapping, right? The black one, the red one, they're overlapping here, right? So it's tracking. Why is tracking? If you just look at circuit, why is tracking? Why it tracks? Because when it is on, the sine wave, for example, is still rising, right? When the sine wave is still rising, it is still pumping charges to this point. It's adding, it's just passing through, right? Because this is on during that logic high for the clock. Make sense? So the sample, the voltage in is always passing and charge out the cap. That's why it's tracking, okay? But whenever you pull the clock down to ground, it's going to stop tracking the signal and hold it for a certain amount of time, waiting for another rising edge later, right? So when the conversion should happen, the ADC conversion takes place. Where? The hold. Why? Because you need a constant voltage. You don't want that one to be changed. When the ADC is working from the first state to the ninth state, it's converting the same voltage. It's not converting like two different voltages to mess it up, right? It's the same voltage, so you want to hold it. Make sense? Yeah, I think that's a software issue, maybe, right? God, it's only one little pixel. Good catch. Why it looks like it's tilted so much, even though there's only one pixel change here? I think it's because you got a.
Oh, maybe it's just an optical.
Yeah, optical. Yeah, visually. If I remove this black line, if I remove it. See? It's perfectly straight. Right? Yeah.
I was really confused. I was like, it looks like it's losing like
Yeah.
5 millivolts.
Yeah. I'm just making this class to be an art class, right? Vision. Okay, so.
It's artwork.
All right, so how do you make that happen? How do you make that less than 50%? That special clock for sample and hold. See, here's the clock sample and hold. That's the timing circuit. How many clocks you want to feed into the circuit?
One.
Just one, right? You want to ask a customer, hey, is this an ADC I want to sell to you? But you need 10 clocks to be put in there. And this one has to be 4 megahertz, 2 megahertz, and 1. Just do it. Not too many. It won't be able to sell it to anywhere, right? Just one clock, connect to the clock or oscillator of the circuit, and should generate all the other clocks for the internal circuit by itself, right? So how to do it? Let's just look at the sample and hold first. How to make that? Let's look at the timing circuit here. So the clock being fed into the circuit is 50% duty cycle or not? No. I mean the overall clock.
Yeah.
It is 50% duty cycle. It's just regular clock, right? Pulses. So that's the internal structure of the timing circuit. And here is a sample and hold clock output. it is a counter. So this is the counter, use the D flip-flops to form a counter, and it counts to a certain number and then stop counting. So design a combinational logic to detect, for example, 1010, which is 10, and then give a pulse or reset it. You know what I mean? So the regular clock is 50% duty cycle. Okay, count until 10. I have a pulse and then reset it. It's just a counter. How that works? It's just a counter, right? A counter is a 50% duty cycle clock in here, like 4 megahertz input to the counter, and the counter keeps counting. These are the outputs of the counter. If it's a 4-bit, it's counting to where as a maximum? 4-bit counter, 15, right? 1111 will be the maximum. What's the next?
0.
Yeah, I'm glad you didn't say 16. Why not 16? You don't have an extra bit. You don't have the 5th bit to hold that one, right? That carry is gone, okay? So it's going to be 1111. And next will be 000, so it's resetting everything. But if you don't want this counter count to 1111 to 15, I just want to count to 10. Why 10? How many cycles do you need to run the conversion? 9. Right? Remember if it's an 8-bit ADC, you need the 9 states to get the final result. The first one is 10000, right? That's the first state of the ADC conversion, the SAR ADC's conversion, and that's a reset. So you do need that clock cycle to happen. So the first one, reset everything to 1 zeros, and then keep doing that conversion until the 9th, you get the final result. Okay? So we don't want to do it. We don't want to sample the second one right at the 9th cycle because it may not be ready. There will be time delays. So we probably want to do it at the 10th cycle. Whenever the 9th, after the 9th cycle, the value is ready to be there. And when the 10th cycle, we sample another one. So you want to count to 10 for the sample and hold. Every 10 clock cycles, every 10 counts, you output 1 rising edge to sample a new data. That's why you see here, it's not a 50% duty cycle because all the other cycles are counting. Only reaches 10 here, so it's do output. If you build it, it's very simple, So you have the circuits in there, you just run it, try to understand this better. And these are all just different combinations of the circuit of gates. The counter is just one counter, count to 15. We only need the 4 bits. We only need the 4 bits of the counter, not like 5 bits or 6 bits. Yeah. Right? Yeah. Because, I just need a 10, 11, or 11 as the maximum counts. So 4 bits will give you 15 as a maximum, so it's good enough. If I have a 10-bit ADC, you'll need a bigger counter for it. So this is a door trigger. And you can see that it is, so the timing here maybe need to be changed slightly, because the door count for the door is 9. So whenever it's ready, it just send it out. You probably want to, yeah, because you remember the doors here, right? because you have 9 other or 8 intermediate values you want to use. Yeah, only whenever you got 9 cycles, you got the correct value, which is the final converted value, right? You trigger it. It's just a parallel in, parallel out, D flip-flops. And you'll send it out to the ADC, to the DAC. Why we need a DAC here? Yeah, to look at if it's a sine wave, right? Because sine wave in, you convert it, use the ADC. Remember, we have 2 DACs. 2 DACs. The first DAC is part of the SAR block, and this DAC is for reconstructing the digital output and to make it into sine wave, so we can verify the functionality of the circuit, right? So in the parallel in, parallel out D flip-flop as a door. Whenever it reaches, you can tweak it a little bit. I mean, I'm using 9 because you need 9 cycles to get the final value, the correct value. Something like whenever you get the 9 cycle, you get a correct value, but it's sending out that value at that moment at the same time. The rising edge arrives at the same time. Is that good or not? I don't know. You have to try. If 9 is not working, try 10. Okay.
When you need 2 clocks. Is that you don't operate on the same clock as the same?
But in that case, if you move this one to 10, I don't know if you have to change this one to 11 or not. Just run it for a couple times and to think about it. So the ones I used here, it works to some extent, right? If you look at the final result, which runs for like 2 hours, the spikes are just I don't know, it's noises or something. So the sine wave is behind this converted signal. This is a black trace, a being. It's overlapping with a purple curve. Sorry, I'm getting a sine wave, but if you zoom in, you'll see the noises here, the differences here. If you change the timing of it, you probably won't be able to visualize the difference just on the curve. If you do the signal processing later, you'll see the different results, errors and nonlinearity from it. It's not that sensitive, you know. But you know, this is the purpose of this project, to let you guys explore some new timing strategies and also different circuits. I think for the comparator and for what else? No, sorry, the comparator and the comparator, timing, and what else? Oh, CDAC. Replace it with a CDAC. Not, I use the R2R DAC here, right? Try to use a CDAC.